Alright, so hello and welcome to another problem. I'll keep my voice low and whisper as I don't want to be rude to my neighbors. But yeah, so today we're going to look at the dungeon game that we were looking at yesterday, return to it. And actually I think I realized something about this problem that I think I have a solution to it. I'm pretty sure. I'm fairly certain. I said solved in the name of the video, but I might have to take that back if I'm wrong. But I think I got it. I'll explain in a minute. What we can do is we could basically just reverse the direction that we were going in. So let me reread the problem quickly. Let's do that. Demons had captured the princess and imprisoned her in the bottom right corner of a dungeon. The dungeon consists of n-by-n rooms laid out in a 2D grid. Our valiant knight was initially positioned in the top left room and must fight his way through the dungeon to rescue the princess. The knight has an initial health point represented by a positive integer. If at any point his health point drops to 0 below, he dies immediately. Some of the rooms are guarded by demons represented by negative integers. The knight loses health upon entering these rooms. Other rooms are either empty, represented as 0, or contain magic orbs that increase the knight's health, represented by positive integers. To reach the princess as quickly as possible, the knight decides to move only rightward and downward in each step. Return the knight's minimum initial health so that he can rescue the princess. Note that any room can contain threats or power-ups. Even the first room the knight enters in the bottom right room where the princess is imprisoned. So I'll give you an example. So -2, -3, 3, 1, and -5. You get, so you need -5, -2, -1, -6 health at least. And then you need 1 more health to start with, so we need 7 health, right? And then dungeon 0, you just need 1 health. So relatively small constraints. This, I believe we could do this in quadratic time with linear memory. And actually, the part that I missed before was that if you consider every path, every possible path, and both the health and the negative required health, we call it negative, quote unquote, negative required health. So if you notice, I was saying -2, -5, -2, but still, like, so there's 2 numbers to calculate when you trace your path. One number is the total health, -5, -2, -1, -6, and the minimum, the negative required health, which is -2, -5, still -5. Still -5, and then jumps to -6, right? So that negative required health is a non-increasing sequence, right? Or non-increasing sequence that's derived from the original sequence. Now, if you go backwards in the other direction, you quickly realize that that becomes a strictly increasing sequence. And it's derived from the maximum health, and so you can actually, what actually ends up happening is you can go from the back to the front, which is what I did originally, but I reversed it. You go from the back to the front using the diagonals, and you can calculate the negative required health, the maximum of the previous 2 choices. So in this case 30, it's only -5, 1 is only -5, and you add 1, so it would be -4 here, and here, and you know, add 1, sorry, you add the amount, the health, so it would be -25, so it would be 25 here, and -4 here, and then here would be, there's only 1 choice here as well, so it becomes 35, and this is -4, this becomes, this one is, so is it -4, this one, so it starts off at 0, by the way, 0, and then this one jumps to 30, sorry, what happens, I'm sorry, I made a mistake, I'm sorry, no, yeah, it starts off at, if it's a negative number, it starts off at a negative value. If it's a positive number, it starts off at 0. This sequence also never goes above 0. So, oh no, I'm sorry, no, let me think. Actually, that's a good question. What happens here? didn't really think about that if it's a negative number at the bottom right. I think the same thing holds. If it's a positive number, you initialize it with 0. If it's a negative number, I think you initialize it with the negative number. But yeah, you add the values as you go. So, but the interesting part is here. So here you'd have 25, here you have -4, but here you would take the minimum of the two and then add the piece there. So, or the larger of the two, and add that piece there. So you would want to take this path down. So this would be 25, so it would be 15 here, negative required health, whereas this one is actually, maybe I didn't solve it. Maybe I didn't. Sorry, the max. You want to take the larger of the two, right? So this one would be -4. This one is 25. This jumps down. Actually, maybe I'm wrong. Maybe I'm wrong about this. Maybe I don't have it solved. I'll be sad if I'm wrong. I'll be very sad. I want to say that you can never go above 0. I don't think that's true though. Huh. No? Maybe I'm wrong. Maybe I'm still wrong. What happens in that case? No, it worked out from my example. Oh, no, it didn't work out. Yeah, you never go above 0. I think that's why. Yeah, you never go above 0. Okay. Yeah. That's okay. That's a little weird. It's a kind of a mind-bending thing, but yeah, you never go above 0. So this is -5. This stays at this will go to, instead of -5, it'll go to 0, and then here it's going to go back to -10, and then it'll go to -13, -15. Yeah, that's how you get the right answer. Okay, I think that's probably why. Yeah, this will never go above 0. I don't know, do we need to go backwards? I was thinking that the reason why I had problems was because I was going to I need to go backwards, but I might actually have to do that too. Hold on. Wait, what? Okay. I don't think this is gonna be right, but we could try it. Oh yeah, I have like a huge amount of stuff in there. So this is gonna be a very long test case. I should have taken a smaller test case. it's gonna be a while. We want oh, okay. I was gonna say. Yeah, that's wrong. Yeah, I think it needs to go in the other direction as well. So we're going to process initial columns instead of rows. Let me actually test this before I get too crazy trying to code this up. Oh, that's going to be annoying too. There's a way to just add, you know what we're going to do? We're going to just create another. Paste that in there and more or less start over. Okay. Should be able to write this pretty quickly. Number of columns, number of rows. Inbounds. R, C, and we're going to say base case if we'll just say if inbounds, could do it this way, if inbounds of A, B, return 0, if memo of key this is not going to be as efficient as it could be. And then finally, we're going to say if A equals number of rows minus 1 and B equals number of columns minus 1, now we're going to return grid of n rows minus 1 and columns minus 1. That's going to be, if it's positive, it's going to be 0. If it's negative, it's going to be the negative value. So it's going to be the smaller of the two. And we're going to say, so those are the base cases. And then the recursion is going to be return grid of A b plus standard. We want the larger of the two values. So if you have -5, -5, actually this would be -5, 0, -4. The larger of the two is the 0. Yes, you take the 0. So take the maximum of, and we're going to recurse, right? We're going to call f. This is also const, by the way. F of, so the recursion is going to be also inbounds too. The recursion is going to be to the right and down, right? So the row is A, so down, and also to the right. Okay, that's pretty much it. Start from 0, 0, call it DFS. And it's going to be, now this is actually a negative number. You're going to add 1 to it, negate it, add 1, and then that could be a very large positive number. So you're going to have the smaller of the two. Something like this. Let's see if this executes. That didn't take us too long to code. That's gonna take too long. I made a mistake. That's not gonna finish. I forgot to Memoise. And I should have used a smaller test case. That's this one. Can we produce a smaller test case? Oh no, that's all right. That's fine. Yeah, we could just do one of these. Oh, see if we can roll the smaller one. There we go. That'll do. I forgot to Memoise before. I think that's all we need. Down to the right, take the maximum of the two. This is never going to be greater than 0. And then, oh, the minimum of these, right? That's kind of, yeah, it's awkward. The min of 0, and then at the end here, if this is a very negative number and you negate it, well, actually, this will never be. I think you don't need to do this at the end. Could be wrong. You just negate that and add 1. Oh. No. I'm not sure where that came from. What? Oh, it's because of the. I see, because I copied it from the console. That's awkward. Can kind of fix that. I don't know, maybe, hopefully. We might need to, yeah, okay. That's really annoying. You gotta copy this into okay, how about that one? Oh. Thought I did that, but I missed that. It's always some small thing that I miss. Hey, there you go. Solved it. I think I got it. Let's go with the one we had before. This is a much larger test case. I could do another 100 and try it before we submit this. So this should be a lot slower than the DP solution though. Oh, you're kidding, really? Oh no. That's true, I'd be really sad. Wrong answer. Oh. How would I spend all that time on the DP solution too? 1662. Okay. Maybe we didn't solve it. Oh no. Oh no. Oh boy. What do we say? It's gotta be 1622. Yeah. $30. So we can head 30 and then tail 1. Apparently it's this one. It's causing issues. Yeah. What happened? I'm still wrong about this, huh? What happens if you just return 0 here every time? I don't think it's correct. So what happened here? How do we think we have to do this by hand? Otherwise it's going to be too hard for me to figure out what's wrong. So I kind of recommend Okay. So it's a good thing we didn't invest all that time trying to figure out the dynamic programming version, because that would have taken forever and would not have been correct. Let's take the recursive version. So what's supposed to happen is we go up from the bottom, right? So 670 is what you would get initially. And oh, let's do this. I didn't go as well as I thought it would. Oh boy. How about that? Let's do it that way. Oh no. There we go. There we go. Let's make it a little bit bigger. There we go. That's what we want to do. Okay. That way we can work with our array. So we want to do. So firstly here we're at 670, right? Negative 670. And that's smaller than 0. So that's the minimum we get, right? That's this part. Now the situation we're looking at is that this guy here and this guy here, excuse me, we take the minimum of 0 and adding this value to these. So that's interesting. So even keeping this at a minimum, we end up with 1 at the end of this. Something's not quite right. I feel like maybe I should go over a smaller test case. These both would go to 0, right? Now is that correct? That's my question. If it's negative, you would add. If it's positive, I think you wouldn't change anything. Or would it? Hmm. 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 I think I'm doing this wrong. I have the wrong idea. Actually, it's a non-decreasing sequence, so it's or not, yeah, non-increasing sequence. I think I did it wrong, actually. I think I'm not right in my thinking here. There's actually an example I'm looking at, a much smaller example that shows this is the wrong idea. Okay. Yeah, just give me a minute here while I'm pondering this. Oh. Huh. Well, that's interesting. So you do add these values, but you never go above 0. So you're bounded above by 0. And so I guess this sequence does. Oh yeah, it does change. I was wrong, it's not non-decreasing. I think it always starts off at 0 though. Oh, I don't know. If it's a negative at the bottom, I'm actually not sure. What if we do just 0 here? I don't know. Maybe we can print these numbers. Okay. Something like this, I don't know. See what happens. So that's Memoise, so that should be pretty good. So 0 all the way at the top. So it's a min of 0 and these two values. So 1, 0, 0, 1. So this shouldn't be 1. Definitely not. Because 1, 0, and 0, 1 is oh, I see. Take the maximum of those two, so -8, and add 148 there. That's why we get 1. I see, because you start off with 146, 48. It's interesting that the second one is just -836. So you can get from -836 all the way down. So you could trace the path all the way down. So negative 678, it's only 3 values each. Negative 678, you can go to, you can come from oh yeah. So we can kind of walk through this data a bit here. So from 54,210, so you can go to 0 from 670. So if you go from 971 to 670, or from 988 to 670, right? That won't cost you any health. So that's good. All right, that's this one, and I think this one, right above it and to the left of it. And then so both of those are 0, and then from here it's negative 940. Here is also 0. Here has a number, a value. Can I trace this out? Let's see. I'll go here, 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 here. So go here and here, 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 here. See if I can trace the path out. Maybe that's best. Because it's just too much to trace it. How about this? Okay. Let's try this one. Okay. So 971, value 0. Negative 345. So this is the path taken. Oh man. Whoa. It just keeps going. Okay. So from back to front is the path. 971, 345. So I went this way. $654, 940. Negative 940? What? Well, that might have something to do with it. How did that happen? What? Oh, I think it's just the order that these were processed in. I don't think this is the path that was taken. Oh, I made a mistake. I did that wrong. Could do UV. I'm actually not sure how to build the path. The winners. How do I do this? How do we get the winning path? Could we add a Boolean? Or, well, we could build the path up to that point. Could do it that way too. Could try that. It's not a bad idea. Get rid of all that. Something like this. memo2, dfs2, we're going to say test. So I'm very sad to learn that it looks like my algorithm is incorrect. So this is going to be a vector of integers, and instead of tuples, ints, it's going to be vectors of ints. And we're going to say so we do a similar thing that we did before. Oh, I guess we need more than that. We're going to have the whole sequence up to that point. We'll also have a number. Oh boy. Ret and test. I'm going to set memo2 to ret. So we're going to do something like this. A, or just X, and T1. And Y of T2. Try to get the sequence of numbers. And then we're going to say if Y is less than X, then, and these aren't going to be, oh man. That's okay. Const auto pointer p1 equals t1. Const auto pointer p2 equals t2. Y is less than x, so we want the maximum. So we'll swap these two. And now we can say ret is grid A, max of x and y. Now memo2 is going to be make tuple of ret and p1, I think, is the smaller, or the larger one is what we want. So whichever one is larger. So initially x is pointing to the larger one. If x is less than y, now y is, now they get swapped. So x is now the, yeah, okay. And we actually want to modify what x is pointing to. So these don't, well, or not x, but t1 should be, or p1. So we can say standard vector v, it's going to be p1.begin v dot push back grid of A z B, and then v is going to be part of, Now I return memo2 of key. Something like this, I don't know. Not sure if that even makes sense what I'm doing here. Which is what we want to try to get the for inbound. We're not inbounds, it's just empty vector. Oh, that could have something to do with it, the inbounds checks. See if that works. Yeah, it's still the same key. What? Oh. Maybe that's the issue. This is so involved. Okay. Expected unqualified ID. Oh. Okay. So let's so print X on a new line, or print out the whole sequence. 1, 2, 3, 4, 5, 6. I didn't get very far. What? So, making my head hurt a little bit here, but what we're supposed to do is we get a number and the maximum path up to that optimal path up to that point. We take that optimal path, and depending on which of these optimal paths we choose, which is going to be the maximum of their keys, x and y, or their returned values, x and y. So we have the maximum of these two. Depending on which path we take, what we're going to return is going to be that same path with, so we want the larger of the two, right? So if maximum, right? So if x is larger, x is smaller, we swap p1, p2, but p1 will point to t1. And then we can use p1 to initialize a new vector. And we can update ret appropriately. And we can push back on v. And we have our tuple, and we return this tuple as well. So this, we went to 960 and stopped. Is that what happened? This is not a very large output. No, I wasn't expecting that. Kind of wondering what happened. So we said 148, -8, 198, 609, 534, 960, and then we just stopped there. So I hope we're done. That's enough of that. I think it's because we went out of bounds here. That's very interesting. Maybe that's why this is incorrect. So if we're not in bounds, the problem is that we actually need to select one of these two. And if we select a maximum and a 0, if you choose the smallest negative value, thinking there's a few ways to do this, but one way is maybe to do this. So this is always just infinitely small. What? Oh. Oh, I didn't mean to do that. Yeah, it looks like it's just going off the edge. Okay, we still got the wrong answer. Oh, there we go. Thought something like that might be the problem. So our logic is right. Okay, that's good. That's a good sign. That's a positive thing. Hey, hey, that is very encouraging. So we can go back to our massive test cases. Try that out. This was a challenging problem, man. This was tough. This upstore is still not done, by the way. Still not done. We'll get another batch of 100 while we're at it. Oops. Oh, didn't mean to do that. Wow. Do another 100 test cases here. think we got it. I think we got it. Yeah, those are pretty much all the bounds. I think we do 200 random test cases. We're probably okay. Probably okay. Alright, I think we got it. Let's give it a shot. Nervous, but hey, there we go. 24 milliseconds, okay. So we did it. But notice this is memoized, right? Very straightforward. Okay, so how the solution works, by the way, let's go over that. So it's actually pretty simple how I worked it out. The example I used was something like this. It was numbers -3, -2, 1, 5, -10, oops, 3, -20, 15, and 5. Okay. So the key observation goes something like this. You realize that if you're going to look at every path going down, then the issue that you run into is, in order to calculate the health that you need, and we're going to use that health as 0, so we're going to call it the health, total health, and the negative required health, right? So each of these paths, you could say -3 total health, -3 required, -5 total health, -5 required, -4 total health, -5 required, -1, -5, and then 4, -5, right? That's this path. That's actually the optimal path in this case. Another path would be -3, -3, 2, -3. Now notice this is a non-increasing sequence. So this is always going to get worse as you go. Then you have -18, -18, -3, -18, and then 2, -18. But we only care about this number in each case. Now the observation that I made that allowed me to actually solve the problem, I wasn't really able to solve it before, is I noticed that these numbers, if you go backwards the other direction, that we don't really care what the total health is anymore. And if we start with a total health of 50, then we would add to both numbers each number we see, but never going above 0 for the required health. So here you would go 80. So here you would say 80. You would go 90. And these are kind of like, the way to think about it would be basically subcases, recursive subcases. 90. And now you have 7, -2, and 4, -5. Now, what's strange about this is this actually mirrors exactly what we had here, right? But the difference is that we don't need to calculate the health anymore. We actually don't care what the health is. We started from the ending health. And more importantly, not only do we not care what the health is, but the only numbers that we need to calculate the secondary number that we're interested in that's dependent on the health is the numbers themselves. In other words, we don't need to pay attention to the total health at all, which is really important. Because before we couldn't really optimize this, we couldn't really excuse me, couldn't really take the maximum of any number. Like we couldn't really, I guess we couldn't really decide between which path to take, which recursive position to take. We didn't really have a recursive routine actually, because we were trying to maximize both the health and the total and the negative required health. But in this case, we can much more easily, we can actually have a recursive formula to get the negative required health. And if we go the other way too, right, so we start off with 5, 0 again, and 20, 0, we never go above 0 for the negative required health. Negative 20, we get 20, negative 20. And really, yeah, this total health is almost irrelevant. We're going to get the same total health at the end because it's just a sum, but we actually don't need to know it. And then we have 5, negative 20s. Actually, no, so here's the part that's interesting. We're going backwards through the paths. So actually, negative 20 goes back to negative 15, and then again, negative 3, we get 2 and negative 18. When we went forwards, we would have negative 3, oops, right? Oh yeah, we already did that actually, what going forwards looks like. And now that's really interesting that you can just add this number. That's not obvious at all. That's like a really subtle thing that you wouldn't notice that immediately, that you can just add the number here to this negative required health. And the reason for that is because what you're doing is, because these are like legitimate base cases, or not base cases, recursive subcases, it's as if you started off taking damage and then trying to recurse on that base case. And so it actually works very nicely. So you would quote unquote reverse that damage. And same thing if you have health. If you started with health, you would reverse that health. It would require less health because you started with more. So yeah, so these are actually proper subcases. And because when you're processing these subcases, you never want to go, you always want to know basically how much health, what's the negative required health to get through that subsection. And so if you took damage, you would need more health, so it would go more negative, and if you had health, it would go more positive. However, it's never going to require you more than 1 life or more than 0, right? At any point, we just add 1 at the end to mimic 1, but 0 is the cap. So that's actually the observation. Key observation is you have to throw in a you have to go top. If you go top down, you would throw in a minimization on 0, right? So you're always negative, and you can increase negativity, decrease negativity, but you can never it can never take you more than 0 required health to get through, which is a very subtle, slight thing, very clever question to throw that in there. But yeah, so this is like a standard DP, but you have to throw this extra condition to minimize. And then obviously we can go bottom up and then DP bottom up through using diagonals. And that'll give us the answer as well. That'll be much, much more efficient because it'll be, it'll be much faster because we aren't going to be doing things recursively calling functions. And it's going to be iterative, and it's also going to be less memory as well. So you don't have to allocate as much memory either. Don't need to use maps and tuples and things, or maps and vectors and whatnot. So yeah, this is how we're gonna approach it then. We can get rid of all this debug code too. Excuse me. This in theory is going to be a lot harder to write, I think. Well, it already is. Oh, look at that. Okay. Alrighty. So, yeah, pretty amazing. Pretty interesting question. Really, really solid question. Really threw me off. Alright. So, we're actually going to process the final rows, final columns first. That's going to look like something like this, where we're going to have the diagonal go from the bottom to the upwards each time. So when we look to the left, we're going to look at yeah, see, that's really tricky too. We're actually going to have the top of the diagonal kind of like move in, and you're going to go, we go to the left, we look at D plus 1 and D. So D and D plus 1 again now. We're going to go back to D and D plus 1, which is going to be interesting. Oh boy. And also this is yeah, it's never going to be larger than 0, so we just throw this min in here. We'll come back to what this does in a moment. So the final columns first. The way we process this is the last element of the array. So we look in the array. We're going to look at, so if we look at these two, let's look at these columns on the left side here. So these last columns we're going to process first. So we have something in our array here. We look here. We want to process only to the right and down. Oh, that is D and D minus 1. Wait. These are down and to the right. Oh yeah. Oh. So to the right is D, down is D minus 1. So it is going to be D and D minus 1. Okay. Yeah, so we can start off at 0. D minus 1. That's so confusing. Ah, boy. Where the indices into our array are going to be. Like there's like a, because the array is only one element, then it's 2 elements, then it's 3 elements, and then it stops at a certain point. We could position the array this way, from starting from 0. and then these two elements. But that would be, as I said, D and D. Yeah, D and D minus 1 is what we want. So 0, D, D minus 1, and then 1, D, D minus 1, and then 0, 1, 2. Right, in this case, it's only 3 elements in the diagonal. And so we would walk from right and then up. Yeah, I guess that's fine. We could do column less than the number of columns, offset is 1, process diagonal. So what gets placed if we do this? It's the diagonals are going to be moving. See, that's a tricky thing, questionable thing. Are we going to go up, over, and up again with our diagonal, or are we just going to go? Yeah, see, the thing is we have to think about if there's excess rows or excess columns. So if there's excess rows, then this will become, all right, we'll move over, process all the rows we need until the last few rows, and then we process those last rows in a special way. If we do it with columns, we process these columns, process all the columns in the same way we process the excess rows, process those columns, and so here we do excess rows, excess columns. There wouldn't be excess rows. Yeah, we have to look at this. This is kind of special. This might be the same, maybe. But I think we do the columns first. Something like that. It's a little confusing. But take our rows or our columns. Let's say we have an excess number of columns. We would process and leave a certain amount. How many rows would we? Now, if there's way more rows than columns, then there are no excess columns to process. So I think we should do the columns first and then do the rows. And then printing the excess rows is actually going to go up. And you're also, I think if we have our diagonal in the right spot, once we process, yeah, but I think the processing the excess rows could just be on the bottom here. I think we don't need this part at all. And we're gonna put our beginning. We're gonna put our initial value in the like the diagonal's always gonna start at the bottom. It's gonna go L-shaped bottom right over the L, left and up, and it's always gonna be in the beginning of the diagonal, the beginning spot. So we'll say initially previous of 0 is going to be grid of 0, 0, and we said it's the minimum of 0 in that value, so the initial value. And so we process the columns, final columns first, or just, yeah, final columns first. Or rightmost columns first. We would say start the bottom row. I don't know if we even need an offset. I think we just start the bottom row, columns number of columns. We probably want we could do min f is better. And Yeah, that's fine. We could do min f. So that'll be the initial starting point of the diagonal as well. So process the diagonal. D will start off at 0. The row and the column, we're going to move upwards. So decrement the row, decrement the column, increment D as well. So process each part of D. And we just have, as long as we're not off the side here, so the row won't matter, but the column immediately, the first one will be off. And we select is, we go 0, as there's upper, lower, is D just has to be between 0 and min f. And yeah, the idea here is that this is just an out of bounds or inbounds, out of bounds check. You actually could do better than this. You can just say I think it's easier just use an inbounds check. Yeah, it's a lot easier just to think about it to use an inbounds check. And then so if D minus 1, oh, I see. That's kind of tricky, huh? I'm trying to think of this. There's a better way to, this is definitely like a better way to set up this inbounds, out of bounds check. I don't necessarily like having like an upper and lower bound. I mean, in theory, you can use that to kind of manipulate like how the diagonal is moving, but I think it's better to just loop through, not have an upper bound and a lower bound, just loop through R and C and say, you know, sort of up the diagonal and down the diagonal. It's going to be if, so we could say int a b, so if inbounds of d minus 1, which is r plus 1, c minus 1, then we could say a equals, we set these initially to can you do this in C++? I don't think you can. I think you can do this in Python, but I don't think you can. Can you do this in C++? I don't do this too often. A equals B equals this numerical bottom numeric limit. So this would be temp, or no, this would be previous of d minus 1. Same thing. And then you're going to say temp of D is equal to min 0 of the larger of A and B. Yeah, this is so much simpler. So much easier. Okay. This is a lot simpler routine, I think. Does this compile? I think there's a huge test cases that we're on right now. Forgot about that. Let's just wait a minute. I don't know if this part's going to compile. compile. Probably should use a smaller test case here. I think we can go ahead and just dump this here. Let's try that again. That should compile. It should probably give us a runtime error. Oh, okay. That's definitely way better. I think you can't implicitly capture n columns and rows as well. All right, so inbound select. Yeah, we don't need to do this checks with the upper bounds, lower bounds, all that stuff. That's just confusing. The upper and lower bounds on the diagonal, I think, is just way too confusing. We just do inbounds checks. So actually, this is row one down, one row, over one column. Rightmost columns first. Process diagonal. We're gonna update D, temp D, override previous with temp. Then we process. I don't need to do this part anymore. Process excess columns. So we process the rightmost columns. Then we want to process. Now it might not be any more columns to process. So this would just exit. So this is going to be. And by the way, this is decremented now. Are we back? Are we live? Hello? Okay, I think we're back. Sorry about that. By the way, this is going to be, there's no offset. This is going to be greater than or equal to, it's going to be number of columns minus minf. So, yeah, that's a little confusing, but it would be greater than or equal to 0, and the number of columns minus minf would mean what's the index there? That's an index. The number of columns minus 1 would be the last position, and then you take minf from, that would be it should be minf total. Yeah, that's a little confusing too, but it's 1 before, so it's the, if you had if you had minf, if you had some variable x, and you said x plus 1, x plus 2, x plus 3, all the way up to n columns minus 1, that range, n columns minus 1 minus x plus 1, would be equal to minf. So n columns minus 1 minus x plus 1 is n columns minus x equals minf, means x is equal to n columns minus minf. Yeah, it's a subtle thing, tricky thing, but yeah, this will give us, if we say equals, this will actually give us minf number of columns from right to left. So we process those first. We process our excess columns, which would be starting off from that position, n columns minus minf minus 1. Right now we're going to the next over. And we're going to say as long as columns greater than or equal to 0. And we're going to decrement the column. Now the tricky thing here is there might not be any more columns to process, in which case we just exit here. But if there are, we would go all the way down. And we're starting off the next index. Now if n columns is equal to min f, then this starts off at -1, so immediately it would exit. And process our diagonals, and we do the same, basically the same thing we just did. DRC being row, column, D. Yeah, it's like the same subroutines. Processing excess columns, and then finally excess rows or remaining rows. Excuse me. Now notice we processed the main diagonal already, so we're going to do one less row than minf. We start off at minf minus one row, and then process the diagonals from there, and the column is going to be 0. At this point, we should be at 0. And row is greater than or equal to 0, and we're going up the rows. And we have the same routine processing the diagonals. Something like this. And then now finally, we say should be 0, something like this. Right, the value at 0 of the array should be actually our final result. Let's try this and see how this goes. There we go. Okay, well, maybe, right? Let's try some example test cases. And then we can run through some of our tests, generate some randomly generate test cases. So I got 3 instead of the right answer. Why might that be? Oh, I did miss something here. Grid of A, B. That's a subtle thing. Oh, it's not A, B, it's row column. I think row column always has to be in bounds. Yeah, this guarantees is always in bounds. Almost. I think this might not be a +1. No, I think it's a plus. I think it is a +1. What are we missing here? we should debug. What is it? Print D for print diagonal. Let's make this a little bit faster here. I don't know, man. Just keeps printing in the weirdest spots. Strange spots. Alright. Just print all over the place. Let's see. Let's see. So initially we have -2. Oh. Wait, what? Oh, this should be... That might be why. The wrong starting point. There we go. Okay, still the wrong answer, but maybe a bit better. So -5, -5. Rightmost columns should be -5. These actually should both be. This should be 0, and this should be -5. 0, 1. So the first, after the first iteration, should still be the same. Second iteration should actually be 0, -5. So 0 should be, it's going to be, so D minus 1 doesn't exist. B would be previous 0. This should give you, what should be -5. So this should be -5 plus 30. This should be 0. This should be -5. Also, I don't know where all these zeros are. Excuse me. Oh, I think all these zeros are from the second one. I don't know what's going on there. Let's get rid of the second one here, because that is confusing. Okay, that was from the second one. All right, that makes sense. But this is not what we expect at all. Should have -5, 0, -5. This should be 0, -10. Actually, no, -10. Yeah, -10. I think it's actually -15. 0, -15. This is 7. This is -5. I think -6. So this is -7. This is -6. But this should go from to -5, -4, -1, and then -6. -4, -6. And that's this diagonal. The 0, you'll end up with -6. Should be -7 here, -2, so -4 and -5. Yeah. -7 and -3. Huh. What happened? This should have been -3 and -2. Should put you at -6. Or yeah, I don't know, -5. I mean, this is wrong, but I don't know what exactly is wrong. Okay, let's try to get the, what do we expect first? First routine, we would print -5, 0. That makes sense. Next should be 0, -5. Because this is going to process this inbound here, and then D0 is the previous, and then D1, there's no, oh, you know what? This is supposed to start off at, there's that too. Forgot about that. I mean, it shouldn't even trigger because it's supposed to be, it's supposed to be out of bounds anyway. Actually, really shouldn't matter. That's a little bit better. But that's not supposed to matter because these would be out of bounds. Yeah, D-1 doesn't even exist. In a lot of cases, or some cases. So this diagonal, when you're processing, looks for down and to the right. So to the right doesn't exist. Down does exist, but so that's a good question. When you process this here, what down is D-1. And D doesn't exist at all. Huh. Which would give you these guys here. And then when you process this guy, down is the previous arrays. So that, oh, so this is kind of awkward, huh? The diagonal shifts to the right as you go up the side. So D minus 1. Oh, that's interesting. Oh, okay, that's kind of a problem. We have to shift our array over. That's really awkward. Yeah, it's very awkward. How does that work? That might be part of what's going on here. I think it's still wrong anyway, but yeah, starting the array off this way, and then the problem is that setting up this next diagonal, to the right is actually D0, down is D minus 1, right is D0, D1, D minus 1. So that works from right to left, but once you start climbing upwards, then this D down is actually minus 1, and to the right becomes plus 1. Yeah, that's interesting. So, I mean, you could add like a toggle or something when you go in the other direction now. And it would be minus tval plus tval, because what happens now is, yeah, you could do, so plus tval minus tval, and same deal here, excuse me. So it would be, I think, minus plus on this side. So if, that's really confusing, but I think it works where if the toggle is on, then actually this is just RC and D, and then this becomes R plus 1 is up 1, and C minus 1 is to the right 1. It's interesting that these swap, add and subtract. Both of these would get bumped one row. I think these actually should both be plus. Yes. These should be the same, minus and plus. Plus moves you to one column to the right, minus puts you one column down, so both these are going to shift over upwards when you start climbing the ladder. Yeah. columns, excess columns, remaining rows, and you'd have toggle is false for the columns. Toggles at the end. If it was not confusing already, things should be really confusing now. What did I get for the solution? Still got 8. Somehow still got 8. Okay. Okay. What is going on now? What is that? Oh boy. Oh wow. Oh wow. Okay. So initially we expect these numbers, and then the first iteration really nothing happens. I think it has no processing of the first iteration. Second iteration, that was where it gets interesting. Second iteration we expect, so we're going to process nothing here and -5 here. We should get 0. So we get 30 plus -5 puts us a 0. So this should be a 0, not a -10. And then the second value, this one, we expect the negative part, -5, and then -infinity, so -5. Plus 1 puts you at -4. So it should be -4 and the 0. That's what we expect here and here. But we don't get that, do we? Now why don't we get -4 and 0? As you can see, this is like way more involved to figure out than the Memoise version. This is like so much more work. It's painful. Okay. Have the row, that doesn't change. The columns, that's the right column. D starts off at 0. Select D and R and C. Row should be 0. Column should be, I think, 1. And 0, R, and C. It should be the same spot. Yeah. Column 1, row 2. So we take 30 plus this maximum of A and B, which should be, so A and B, so D minus 1, so that's just this one. But this one is in bounds. R and C should be in bounds, right? T-val is 0. So this B should be 30. 30 is definitely larger than -infinity. So take the minimum of 0 and 30. which should be 0. So temp D is 0, which is 0, so temp 0, 0. And override previous I equals temp I. Then we look at 1. The next D is now incremented to 1, right? So row and column. Row is decremented. Column is incremented. You should go to this spot. And then select again. So 1 or C. 1. Minus 1 should be, now this is previous we're still looking at, right? Not temp yet. It's previous. Toggle is false, so we have, oh, that's interesting. Right, increment the row by 1 and decrement the column. Now that's interesting. Yes, that's the position. So actually, this is interesting. This is actually going to be, oh, this is not inbound. Oh, that's why. Okay, that's confusing. It's actually just R plus 1, same column. Yeah. That's the one below. If that's in balance. And to the right is just C plus 1. So that's really confusing now too. This T-val. Do we need this T-val? Probably not. Well, yeah, if it's down and to the right, that's actually always the case. But the problem is that down is oh no, down to the right is always the same thing. It's always down would be no. So the right is 0. That's the problem though. So to the right is 0 for a while, and then down becomes 0. That's why you gotta just shift them over. But you're still down and to the right, so it's just R plus 1 is down, and then to the right is C plus 1, I think. It's always the same thing. R plus 1 is down, C plus 1 is to the right. Those are inbounds, you can use them. And then the representation in the array is if we're traversing columns, then it's just going to be D, it's going to be D minus 1 is down below. And if we're traversing, and then to the right is D. And then if we're traversing upwards, then below is D, and right is D plus 1. That's really confusing, but yeah. Okay, that might fix a few things. Wow. All right. Still quite a bit of time again, but we're okay. Signed integer overflow. Excuse me. Whoa. Whoa. Okay, so we get both A and B. Come on, man. It's great. Because both of them are out of bounds. Alright, so we skip the first iteration. Skip the first row. Let's go ahead and skip that one. That's funny. That's good. That's good. Alright. A little bit better. Almost. Almost. A little more of what we're expecting. So column 2 is skipped. Column 1. Yeah, because what you end up with is you just end up with 2 infinite values and you try to add -5 to it, and you're like, what's going on here, man? What are we doing here? You just initialize it with that, either 0 or -5, depending on which one's. Oh, actually, this should be, yeah, which one's smaller. So you get, yeah, so first processing, print column 1. So that's interesting. Before we process column 1, kind of want to print what it looks like after the process. Yeah, so we print twice. It had nothing processed yet, so we should actually probably put these after. I think it's a little more appropriate rather than before, so that we're not so confused with what's being printed. All right. So initially, this is what it looks like. Then we have 0, 4, -4, so what we expect. Then it should be 0, -10, -1. So this one's still 0. -10, right? Yes, -10, because we picked 0 here. And then up here, though, we have -1. Now, things get a little bit hairy here. Now we toggle, and we process the, so there's no excess columns to process. So process these remaining rows. All right, this should just exit immediately. The row is minf -1, so minf is 3, so row is 2. So we should actually subtract 2, excuse me, because we definitely already process. Oh, there we go. Okay. So it looks correct. Could comment these out. And all these debug statements. And then start going for much larger test cases here. Okay. What's TT2 look like, or TT1? I got 100 lines on TT1, and how many on temp A? Okay, we're gonna do TT1 and then temp A. Let's give that a shot, see how we do. And my connection just it's nailed. I try to run this. I think it's running locally, which is kind of weird. Let me test something while we're doing this. Okay. How did we do? Wrong answer. No. 99999. Oh yeah, same deal, 1622. Two, three, five, 1622. Let's take a look at this one again. Is this 30? Is that number 30? I think we did this last time. Okay. Do we have the exact same error? The same problem. I think this time we checked it. Oh yeah. What? I think we have to set previous of I to, or yeah, previous of I don't know. Temp of I has to be set to all min values after each overwrite. That could be it. One, two, three times. Okay, we have 3 loops. This also could be the, nope, that wasn't the issue. I think this is the issue with I think I know what the problem is with this one. I think this has to do with processing the right number of columns and things. So we can actually we can add back the these print statements. It'd be nice if I could set these loops up properly, I guess. Oh, this just stops, huh? This has got a lot of rightmost columns. So this has a lot more rows than columns. Excess columns, remaining rows. Oh, this could actually be n rows minus 1 minus 2, I think. There we go. I was gonna say, I don't think this. Another question is, does this still work on the other shapes for our test cases? Notepad A. Oh boy. Oh, what a challenge. What a difficult, challenging question, challenging problem. Very interesting. Very interesting. Couple hours. Yeah, this would take a while if I had to do this. Oh, I think we got it. Ta-da! Was it TT3 or was temp A, I think was the one. I guess I'm curious about is if there's a better way to write this. Breaking this up into 3 loops. Very interesting. Oh, I think we got it. We're not super fast, but I think we got there. Don't need a map anymore. Can get rid of our debug code. I would say that's a very confident solution. Okay, one more time. Oh, I forgot how big this test case is. It's an enormous test case. So I guess one question would be this selection routine. Yeah, like we could copy this code for other sort of rectangular based solutions, but I guess my question would be how, like, can we do this more efficiently? I think we go for it. And I don't just mean efficiently like in terms of how fast it'll be. Hey, there we go. Very fast. But I mean in terms of not just how fast it'll be, but in terms of how quickly we can code it. Also, it doesn't seem like we're going to be able to get much faster because of another issue we run into is like we're using all these lambdas. Like we could inline this code, I guess, but that might make it a little bit faster. Yeah, it's going to be hard to be much faster without inlining these routines. Also, these if statements make things a little more challenging too. I don't know if you can avoid these if statements, quite frankly. Yeah, this is tricky. I think we can, I don't know, man, it's probably as good as you're going to get. I mean, this is only two pieces inside of one larger piece. We won't be able to get 100% with this, even though this is extremely fast. The reason we won't be able to get 100% is because of all the function calls in between. If we could inline these two, then maybe we can give that a shot. How about this? This cannot be implicitly captured in this context. Really? Oh, I see. Cannot be captured by reference. Oh no. Oh. What? I guess we could have a pointer to this, I suppose. call it T. I just want to see if this will work. Oops. Inbounds argument. Inbounds is not const. What comes first, n rows or n columns? This is very interesting. I'm very curious if I can inline these functions, or this function. Okay. Is it still correct? All right, a little more memory is being used. Yeah, interesting. It's not much faster though, but you can inline, I think. I think it'll inline. All right, and we want to inline select as well. So let's try that now. If we can. So these are all references of previous is a this is int array previous. This is int array temp. This is grid. Standard vector of vectors. This is int number of columns, int number of rows. All right. And then you have the next set of the actual arguments. Oh, so this is RC toggle, and you don't need this anymore. And you can just say inbounds. And and now select is, what are these arguments here? Previous, temp, grid, number of columns, number of rows. I don't know, man. I think you're better off using the lambdas. I don't think this will make it faster. That's what I'm going for. I want it to be quick. I would like it to be quick. So these are all constants in the front. Ideally, we're going to inline though. Ideally, we're going to inline though. Okay. All right. What does this do? Does this work? Oh, it still works. Let's see if we submit it, it still works. Ah, there we go. Ah, very good. Can I do that? Can I do that? Can I do that far away? Just do a slight bow. 100%. How you like that? How you like that? Hey, it only took 11 hours, but we got there. So you can write a fairly complicated inline inbounds. By the way, this is basically how you would handle one way of handling a dynamic programming solution that you can use recursive memoization to solve this very quickly, and then you can use this approach to actually optimize the memory and the two things, help optimize the memory and the speed and make it iterative, and you have linear memory instead of cubic memory or quadratic memory. And you can use this approach in general. Only a little bit, teeny little bit faster when we move these things out, so we don't have the function calls anymore. There are some branching factors involved here too, so that's why it's a little slow. Oh no, yeah, the if statements make it a little bit slow. I don't know if you can avoid that though. I think ultimately, yeah, it's kind of tricky. There's like a couple branches going on here that makes it a little bit more challenging, but you can still get the optimal time bound on this. So yeah, quadratic running time, linear memory. You make an L shape, and you have 3 loops. So it's not too hard to construct this. You have 2 raw loops. So the first raw loop handles the rightmost columns first. So I'm actually going to save this code, by the way, because this was really interesting. I'm going to close all these extra test cases. What was this, dungeon game? Yeah, we'll get the description here. This is a really good game. I mean, really good, not game. Excuse me. This is a really good question. I thought this was great. This was extremely challenging, and I'm grateful we got it. We got it the first time around, I think. So that's good. That's positive. Hey! Optimal memory, optimal runtime. Yeah, so pretty good. Let's, I guess we'll go on the next thing. I don't know, I kind of want to just like take a moment and just breathe after that. That was pretty wild. But the key insight, there were a few key insights. So first thing is, there's like a lot of pieces to this, quite frankly. The main thing is realizing a couple things. One, that you can set up a dynamic programming solution if you consider that the health, the negative required health never goes above 0. And so the recursion would be, can you get through this part of the dungeon? Can you get through that part of the dungeon? Which one requires more health? That's basically the recursive, the recursive question. So it's not just it's not kind of your standard simple approach where you would say, like, you know, take the maximum sum or something. Like it's more like a property that you're looking for. Like, can I get through this part of the dungeon? How much health do I need to get through this part of the dungeon? How much health do I need to get through that part of the dungeon? And then depending on which, if you gain life at this point, then you would say you don't need as much health to get through those parts of the dungeon, so this would be less. And then the other side of it is, if you lose life, then you require more, right? So that's the logic. So that's very straightforward, and you can very quickly solve this problem using recursion and memoizing that, and then you can use dynamic programming by creating sort of an L shape and a diagonal. So because of the shape of the matrix, it's rectangular. You can do the beginning columns, then any excess columns, and then all of the rows that are left in one shot. And you want to break up the columns and the excess columns into two pieces because you actually probably could just do all the columns first. Now I'm thinking about it. That simplifies things a lot. Yeah, I was doing some funky, strange stuff with my arrays and diagonals and things. I'm actually curious now that we're talking about it. Now we're thinking about it. I think you could just do the columns and then the rows. Yeah, because the issue that I was having was that I was trying to put things and piece things together so that way, like, moving around the diagonal wouldn't be too complicated. But actually, it's fine to just add a boolean and then just make the diagonal the bottom, the bottom beginning the diagonal, the bottom, so the right side, and then just kind of move. So the bottom of the diagonal is always going to be on the that L. I think this works. Let's try that. Hey, there we go. Okay, that's sweet. So that's pretty good. So you can do just process columns, process rows. Just have to have one skip because of the just one skip because of the how this is coded. Where we take these minimums. Yeah, super simple. And then you can inline. You can write this code out first and just check to see if it works, and then inline, as I did to speed it up. There we go. Let's try again. Okay. Was it faster when the two loops were? I don't think so. And then actually you could inline, when you inline this select part, you could change this, what is it, this toggle. You could do that manually. So if you could copy paste this code in line too. That might be a little bit faster. I'm gonna just keep trying to see if I can get, yeah, it's kind of random what you get for the memory and the speed. We got 0 a few times before. Let's try one more. How you handle this internal part, it matters quite a bit. It matters a bunch. So this inbounds part. Yeah, the tricky thing is like, I don't know, I'm not able to get 0 milliseconds again. I'm annoyed. I want to get a 0 milliseconds. So this is pretty good. That you only need to write these parts twice, 2 loops, one for the right side, one for the row, one for the columns, one for the rows. You just have to skip one row, right? One diagonal on the row for the row, and trying to get slightly faster. It's kind of random, I think. What else do we need to do here? think haven't rolled 100% in a while. You could actually copy paste this code directly in to these two loops, the select and the inbounds, although I think it's better to write them as functions like this. I think this is fine. Tricky thing is just thinking, is there a way to avoid these if statements? I don't think so. I know we had them before, but like, how do you... The toggle's pretty good too. I don't know, I like how this is set up. May not always get 100%, but it's pretty good overall. Like, it's just two loops, relatively simple to put together. Skip one iteration, first iteration, because you're going to set that up yourself. Skip another iteration because there's a diagonal for the columns that you just don't need to process for the rows. So one row, just remove one row up, and yeah, process the columns, process the rows. Just have to toggle your diagonal on the rows, so that way you instead of going for, when you're going down to the right, you do down to the right becomes D and D plus 1, whereas before it was D minus 1 and D, where the right side was D0 and now down is D0. So that's like the one slight change when you go up the rows. But yeah, you could copy this for other questions. Like, it's pretty straightforward to routine to write. Just have a selection routine for which one you pick. Process the diagonal, and then overwrite. Overwrite your overwrite the arrays that contain the diagonals. Yeah, it's going to be kind of challenging to get like absolutely zero, but you could write this pretty quickly. I think the DP. I think it's better to write the recursive. I think it's better to write the Memoise version first, just to check to see if it's correct, and then you can go into because I think it's a little bit easier to write. We kind of went through that. We still have it down here. Yeah, it's a little bit easier to write, and then you kind of check to see if it's correct and it works and all of that. And then once you've got this set up, then you can improve to make things a little bit faster and to improve the memory. I think that's the optimal way to do it, optimal approach. Like, in general, that's like the approach for all these sort of LeetCode hard questions, which are some variation of like a DP or DP question, memoization questions. They all kind of have this similar form. I do think if you're dealing with more than, like, this is if you're dealing with like quadratic time questions. If you're dealing with like quartic or cubic questions, then it's a little bit more challenging. I think it's a little harder to kind of understand like how to optimize for the memory. Excuse me. Yeah. Like there's a excuse me again. There's a question that I was working on that was quartic, because quadratic you can kind of think about like the diagonal and like using the memory for just the diagonal, but there was a quartic time algorithm that I was looking at that was memoization not too recently. I was looking at that and I was like, how can I optimize for the memory on that one? Also, another idea, oh, this is interesting too. I didn't think about this. You can make this even better. So like this is if you can't really think about how you might do this other than using the diagonal. But actually, you might be able to just be able to use the you might just be able to go row by row. If you take the bottom row, and from right to left you could process, you just need the previous value on the right. And then when you go to the next step, you can process both the value below, which is itself from right to left, and the value on the right. So it's either itself or the value on the right, if there's a value on the right, if there's a self, if there's something below, either itself or the value on the right. It's basically how you would do it if there's a value on the right. And that would actually give you, that would be a lot simpler to take the memory for the row. Now this is optimal memory regardless if you have more rows or more columns. But that's a lot simpler to code. Just thought about that too. Didn't realize that that's super easy to code. That might be actually faster because of you don't need to have these functions and if statements and things. Well, actually, you kind of still do need these if statements, but it's a lot easier to code that, I think, than it is to code this approach. Let me try that one too. Now that we're talking about it. Let's see if we can do that. That's actually just one loop straight across from the rows upwards. Let's do this. Yeah, it's even better. That's like a little more generalizable too, I think. In the sense that like you can, a little more generalizable in the sense that like you can way more easily code that, and it also applies to matrix type questions that are just like this one. Let me see. So we have another DP version. So we're going to say int previous, and actually you don't even need, you can just say DP. So we could do, we'll do the row by row. So DP of number of columns. And we'll say DP of I is going to be that, exactly that. Number of columns. And then we'll set the previous of, it's going to be all the way to the right. So it's going to be DP of number of columns minus 1 is equal to this value. So this is the starting value. And now you're going to say for int r equals number of rows minus 1, rows greater than or equal to 0, decrement the rows, move up the rows. I'm going to say for int I equals, it's going to go from right to left. We're going to say n columns minus 1 to I is greater than or equal to 0. Decrement I. And you're going to say dp of I is going to be equal to the following. So we're going to have const int x is going to be standard maximum of 2 values. So we have this sort of the same thing going on where if I plus 1 is less than yeah, this is tricky thing is you do want to process each one. So you do I plus 1 is less than n columns. We could just do A and B. So same kind of deal, A and then we're going to say A is equal to dp of I plus 1. is, and then B is always going to be available. Right, so the first thing is, oh, that's interesting, okay. I guess you have one extra iteration. Actually, even the initial value is and we say this is going to be grid, grid. So we don't even need to do that. We could just go right to left in one iteration and just start from the top. And we can also do the right side upwards too. So we don't even need to have this if statement here. So C is going to be number of columns minus 1. R equals number of rows minus 1. R is greater than or equal to 0. Decrement the number of rows. Yeah, we'll explain this in a moment. So this is going to be grid of, we have the same thing here. Let's just do int R. We should actually just do RC. So number of columns minus 1, RC. And same deal here. So this is really interesting what we're about to do. They both start in the bottom right. And we say it actually can start, this one can start to the left. So column minus 2. And this can start one row above. And what we're going to say is RC. And we're not going to set these. Plus, it's going to be standard min. So normally you would take, there's a bottom and a right, but when you're going up the right side, you're just going to take the bottom below, which is exactly dp of, that's the maximum you get. And this is going to be min 0 plus dp of, this is actually going to be the last value, so it's n columns minus 1. Oh no, we can't do it this way. No, never mind, I did that wrong. Okay, I take it back, can't do that. Never mind, you can only do the first row. But this can be standard min of grid plus dp of I plus 1. I was wrong. I couldn't quite do what I wanted to do. Yeah. So we go right to left. Oh no, C. Let's say C instead of I. Yeah. So dp of C plus 1. So yeah, right to left, we know what that's going to start off looking like for the first row. Yeah, tricky thing is we can initialize, we can actually do this. This is fine. Could do it this way. So that we don't have our, this is just so we can avoid the, this is just so we can avoid the extra if statement in our loop. So now we can say, so we'll always have dpi plus 1 always exist, and then dp of I. So what's interesting is dp of I plus 1 is always going to be the right side. And dp of I is going to be always what's below. And what's super interesting is that we process the bottom line. The next line immediately is going to process the bottom. And then the value, the next value there already has the bottom and the right. And so that can be processed. And then the next value also has the bottom and the right. So that's really interesting. So take the maximums of those two values, add the grid of R, and C, or I, really, it would be. And then you just have to make this the minimum of 0. And that is going to be dp of I. So that's super interesting. And then you can return dp of 0 at the end of it, I believe. Now, how is that for a fast solution? For a quick solution? Oh no. Oh, I see. I'm actually not sure we need to do any of this. We may not even need to do this initial value. Does this work? No. Okay. Alrighty. Yeah, this would be a lot easier to debug in code and whatnot. So it's super close, but so from right to left, you have negative infinity, more or less, and you're going to say this is 0. Oh, I think it's... Yeah, this is... You don't go above 0, never go above 0, but you have dp, this value is going to be, so I, what's there and what's to the right. In this case, oh, the initial value should actually be, well, this initial value would be -5 plus the maximum of these two, which would be, dp of I would be 0 initially. I think you do just need to set the first one. I think the first two is sufficient. Or it might be, I don't know. Oh yeah, that's all you need. That's wild. And then you just negate that and add one. That's astounding. Oh man, that's a lot of fun. Wow. I have to say I'm definitely I guess I'm proud of myself with this one. Oh, wait. Hold on. Do we need to do this? Hey, there we go. Yeah, I was gonna say the only reason we had to do the first one is because we skipped a skipped a row. What's going on there? The 0 and what? What's that printing? Wait a minute. What is going on there? Huh. Oh, there's two there. I get so confused. How do you like that? Now that is a clever solution. If this works properly, which I think it does. Oh no. Oh wait, what? Oh. Oh, wait a minute. Oh. Wait, what? Does this not always work correctly? For some reason, if I deleted the debug statement, it was not correct. Oh, look at that. Wow. Really? That's pretty wild. Oh, man. Whoa. Whoa. So the debug statement makes it correct? What is going on here? -5. Does this always give you the right amount? If you move the debug out of there, it doesn't work properly anymore. I think it has something to do with what the values are initialized to. Yeah. That's interesting. I think I just need to initialize the values, but part of me thinks like it's not necessarily a big deal. And not initializing, sometimes you just get weird things. So no, this should initially be if we remove the debug, and it doesn't work properly. That's so weird. I think we just need to have a quick routine here. I think that's all we have to do. Just initialize these values and then it won't look crazy anymore. There you go, okay. It's like, what is happening? Yeah, I was hoping actually the first call would, but the problem is that you call this max on dp of I and it gets a little weird. Okay, anyway. So we can, but if you really wanted to, you could rewrite this first loop here. Actually, maybe I should do that. So we'll do one less loop here, and we'll actually run this dp here. And it's going to be I think that works too. No, this doesn't work because no, this doesn't work. Well, you could say the max is always just dp of I. You could do it that way. I think that works. Oh no. I'm so confused. Yeah. But the problem with this is then you run into an issue where since this is infinite, this is going to give you a problem. We're really splitting hairs here at this point, by the way. But since this is infinite, if you add a negative number to this, you'll have an issue. So you have to throw in some if statement here. Okay. But what you could do is actually set the first value as well. Which is going to be the minimum of 0 grid of number of rows minus 1 and number of columns minus 1. And then you could just set this to 1 less. And then that should work properly. And that's better. It's mo better. That's better than the first initialization routine to just 0. There we go, I think that's correct too. So now we can, this actually doesn't need to be set anymore, by the way. Oh, wait a second. Oh yeah, no, we do want to set that. I'll take it back. All right, I'm fine. We're correct. That should be. Yeah, because every column, this just will never be changed. This will always be at the top. Or every row, rather, the whole column. Let's take some test cases so that way we don't get ahead of ourselves here. Alrighty, let's see it. So this would be a much faster solution to code if this is correct. Use a little bit more memory, but way faster to program and to think about and whatnot. No, it's wrong. test case, okay. No. What did I do? What did I do? Ah. Okay. So something's wrong. So this is ideally what we would code in like an interview. You would want something like this if obviously you'd want the correct version of this, but if it were correct, this is what we'd want. So there's only 3 rows to go through, okay. We got 5, 30, 43, and we expected 1429. So we could just take this and put this into a notepad doc here. We can actually pretty print this with our that's kind of annoying. There we go. That's what I wanted to do. I wanted to look at it without word wrap, and it's just three rows. So this was wrong. Okay. I wonder why though. So let's see. What path would we take here? So what's interesting is we're processing the bottom going up, and each diagonal can be processed, right? Because we can be processed because we can get negative 74 here. We get everything all the way to the left. We don't have to initially we don't have to process anything below. So we can just take whatever we have to the right, dp to the right, and add our grid value to it. And then yeah. And just take the min. It's never 0 though. That's the only thing. It's never 0. So they should all just be negative numbers. It's going from right to left, so these are kind of backwards. Oh, that's interesting. Wait, what? Oh, there's only two rows that get printed. Could also make this its own routine. Okay. numbers. I'm not sure where these came from. Oh, I see. Okay. What's weird about this is, those seem like garbage numbers. That might be why this is wrong sometimes. Yeah, okay, that's garbage, it's coming out. Okay, but why? We get these numbers, and then we get row of dv plus 1, the min of whatever's there in the row, which is the bottom row of the grid. And we're taking min of 0 of that plus dp of I plus 1. Oh, that's why. I see the problem. Duh. It's supposed to go from right to left, not left to right. That's kind of a subtle thing. Not that subtle. Really not that subtle, but easy to miss. Certainly easy to miss. Yeah, that goes back to, I mentioned that before, we would overflow. That's why we want to set this one manually. There we go, okay. That's what we're after. Beautiful. Yeah, that was kind of embarrassing. I just forgot, man, I don't know. Forget sometimes. Made a mistake. We don't need those anymore. Okay. Notepad, exe, temp, A. There we go. Now this should be a much more succinct and beautiful and fast and efficient. The memory won't be as efficient as it could be. But this is a really good solution, I think. This is super fast. And actually, if you really wanted to, you could actually, you could swap the solutions based on the rows and the columns. So you don't have to do this row by row. You could do this column by column as well. You can actually swap the way that I think it was T21 is the other one. If you wanted to, you could swap how this is being processed. So you would process column by column if there's a smaller number of, very small number of columns, and row by row if there's a small number of rows. I don't know, column by column if there's a small number of rows, right? If the number of columns is, yeah, column by column if the column size is small, row by row if the row size is small. So you reduce the amount of memory you're using. So we can be fairly confident this is correct, I think. 200 test cases is probably correct. Now, this is really fast, but it uses a little bit more memory, if you notice. Slightly more memory. But this was really fast to code. This was extremely fast to code. Coding this in such a way where it would swap depending on which one's larger and smaller, that's a little more challenging, I think. I'm not sure exactly how to, I mean, you could write an if statement if you wanted to, but you would need, oh man, no, too soon, okay. But yeah, here we go, we have our solution now, and this is a super efficient solution in terms of coding it. Really fast to code this. This is a great DP. I don't know if I can really go faster than this, quite frankly. This is like as fast as it gets. Yeah. I don't know, seems like there aren't really many branches in here. I mean, I guess you're calling these functions a lot. Maybe you can optimize that, but this is all I got, man. I don't know, how do I... There's literally no branches here. No branches at all. There's just the min and the max functions, that's it. I actually don't know how to make this faster. Like, this is as fast as I think as it goes. It's really just random whether or not you get the sort of the fast iterations, I guess. So yeah, this is how I would do it in the future. Again, you can, like I said, you could modify this to, if the number, depending on if there's more rows or more columns, you could run just an entirely different routine. You could put one if statement in there if you wanted to, and then you'd have optimal memory. But yeah, really interesting question. But yeah, if you have matrix questions like that that are either down and to the right or like up and to the left or anything like that, then you can actually go row by row or column by column as part of your sort of dynamic memory is your DP solution. And it's like ridiculously fast to code it and ridiculously efficient. Yeah, brother. If I realized this solution sooner, I would have been so fast. I can't believe I spent like so many hours on this too. Like how crazy my solutions went. We had this one, and then this is like just super succinct. So yeah, we'll run one more just for good measure. But yeah, we spent like many hours on this. But the thing is, if we run across problems like this again, and you have to remember that there could be kind of special conditions involved where you minimize or maximize things. You almost always, almost certainly can modify things in such a way where you can DP like row by row or column by column and have no branches at all, no if statements. All right. I'm very satisfied with this solution. This is great. All right, this is good. This is solid. I spent forever on this, by the way. So there's that. Let me just save this because I'm kind of proud of it. I mean, the idea would be that all of our other solutions we want them to look like this. We want to be able to code them that quickly and want them to look like that. I think it would be really challenging. I don't know, like takeaways I'm looking for here. Like, I'm looking for other kinds of takeaways here. So, I think the recursion that we should go with is, this is the recursive idea. Take the negative required health, right? And that'll tell us how much health is required to get through the dungeon. If we can go down, there's a certain amount of health required to get through the dungeon. If we go to the right, there's a certain amount of health required to get through the dungeon. Take the smaller of those two, or the larger of those two. Excuse me. If they're going to be negative values, negative numbers. So take the smaller of those two numbers, or if they're negative, you want the less negative number, which is the larger. Take the larger of those two numbers. So it's the negation of the required health. And then the required health can never be more than, the negation of the required health can never be more than 0. Then we can add, either if we gain health where we are, then we can add to those two values the amount gained. If they're negative numbers, add that amount. So now it's less health required. If it's negative, we can add that as well. Now it's more health required. So we just add our number directly. However, the amount of health required to get through a dungeon can never be more than 0, right? Because it's always negative. So we lock at 0 by taking the minimum, as you see here. So that's like the key observation. And then from there are like myriad different things you can do to quickly code this up or code this up in a reasonable way. Wow. But the observations that you want to go through through the dungeon, health through the other dungeon, and also require that the health is never going to be less negative than 0. So it's always the negative required health, always going to be great. Now we could actually make these numbers, like we could go the other way around and like use positive numbers for the amount of health required and negative numbers for the amount of health gained. But I think that gets really confusing, and it's unnecessary to do that. It's easier to think about it that way, but we don't actually need to make that switch. So there's like a couple things here. The recursive idea is very important, and the other part is realizing that you want to use negative numbers instead of positive numbers. So it's going to be the amount of health is going to be a negative number, the amount of health required. And you can never require more than 0. And because they're negative numbers, you want the larger number rather than the smaller number. We could make the health positive, so that's the amount required. But I think, as I said, it gets really confusing if we do it that way. So yeah, those were some of like the key observations. And then you also realize, hey, we can go row by row because this is a matrix, so we only need the bottom row each time. And we always get the right to left using the bottom row. So yeah, I'm really satisfied with this. I'm like super satisfied. So this is great. This is enjoyable. I'm gonna stop here. I think I'm just gonna go to bed. Like, this is super interesting. It's very interesting, but the problem that I have is it's just how much time I've spent on this already, and going into other problems, I kind of just want to like take a breather. So yeah, this is very enjoyable, very satisfying, and we'll move on. So yeah, thank you for watching. Talk to you soon. Have a good rest of your day.